Everyone out there has a groovy tune that they like to listen to. However, have you ever thought about the science behind that ear candy? Well, I mean like about the sequence of notes and even the sound waves. Well, here's your chance to find out. So, what is a wave? A wave is defined as a disturbance that is propagated through a medium or space, meaning that when a mass is disturbed, it will vibrate. When we take a simple oscillator, like a spring, with weight and vibrate it to simple harmonic motion, or when the restoring force is proportional to the displacement of the mass, the motion can be graphed as a sine curve. So, looking at this graph, there are important properties of this wave to map out, like the amplitude. The amplitude is defined as the mass's maximum displacement from equilibrium, or from resting position. You can find the maximum of the graph by calculating the amplitude and the minimum of the graph by calculating the negative amplitude. The period is known as the time it takes to complete one cycle of an oscillation, or how long it takes to get back to the same point. The wavelength is the same thing except it's measured in length. Even though we could stop here with the sine curve, let's get into more detail on why the sine curve is so important. Sine is a trigonometric ratio of y's length, the height, divided by r's length, the hypotenuse of any right triangle. We can apply this function to the unit circle, a circle that has a center of 0, 0 and a radius of 1. This circle is so significant because any right triangle ratio can be graphed here, and it also gives the coordinates, degrees, and radians for certain points on the circumference, and even vectors when making a line from the center to that point. When we try finding sine of a certain degree or radian on the unit circle, r becomes 1 because of the unit circle's 1 unit radius. Since anything divided by 1 equals itself, sine now becomes a function representing only y, or the height of triangles. Now when we graph sine of theta, or the function y equals sine of x, in radians instead of degrees, we get a sine curve, where y represents the displacement of a vibrating object from the x-axis. From this graph, we can identify many properties of the wave, like its period and wavelength, and amplitude. This is why sine is so important in calculating the properties of sound waves. However, let's take this graph one step further. To really attribute this graph to a sound wave in physics, we have to change the axis so that the y-axis can have units in length to measure the amplitude, and the x-axis can have units in time to measure the period, or units in length to measure the wavelength. Not only that, we have to replace the transformation constants in the original sine formula with constants for the wave properties. Also, remember how sound waves are longitudinal? Therefore, they have to have compressions, regions with higher densities and pressures, and rarefactions, regions with lower densities and pressures. So just note that they exist in sequences on the sine graph. Frequency is also another vital part of waves. It can also be calculated by finding the inverse of the period and put in units of hertz. So if we wanted to find the frequency of a wave that took only 1/100th of a second to go through one cycle, or a period of 0.01 seconds, that wave would have a frequency of 100 hertz, meaning that it would only take that wave a second for it to oscillate 100 times. Pretty cool, huh? You see, Frequency applies to music because all the different notes in music have specific frequencies, and in different intervals, they can make pretty cool tunes. For example, let me play the C major scale. This sequence of frequencies or notes is called a scale because there are certain increments between each note. However, when we start mixing notes together, some notes sound good together, like, and some not as good. Well, so really, why is this? Like, why doesn't every note sound good because they're in the same increments of a scale? Well, this is because some notes together form vibrational ratios. Vibrational ratios are the simplest possible ratios, like 1 to 2 to 3, 3 to 4, etc. and etc. between the frequencies of each note. For example, remember how the same note an octave higher was twice the frequency of the same note an octave lower? This is because the fundamental frequency when played on an instrument was halved. So, for example, let me play C on the string. So when I play it, it forms the fundamental wavelength. However, when I halve this, when this is halved, we have the wavelength, or the area of the string that is able to be vibrated. So therefore, when we have the wavelength, the frequency doubles. And so since the higher note is twice that of the general overtone, then these two notes form a 1 to 2 vibrational ratio. And so together they'll sound like. Pretty cool, huh? Let's take another vibrational ratio, for example, like the tonic of a note and the dominant. So when I played on the same string, this is C or Do, and this would be G or So. Notice how the string can be in 3 parts. And when I cover up this part of the string so that G can be played, it's cut into 3 parts, and 2 of those 3 parts are being played. So this is forming a 2 to 3 vibrational ratio. And the same thing can be done with Do and Mi. So we'll play C or Do again. And then we'll play Mi over it, or E on the C major scale. When I cover up E, it's the C string, which would be 5 parts, or the whole string. When I cover up E, then we're preventing one of those 5 parts from playing, forming a 4 to 5 vibrational ratio. This is how vibrational ratios can really make music extravagant.